You've probably seen this, right? You're driving on a super windy day, the trees are bending over, and yet those massive wind turbines are just standing still. And you think, wait, what's the deal? This should be their time to shine. Well, what looks like a paradox is actually some incredibly smart engineering at work. So let's get into it.
I mean, that's the real question, isn't it? These things are built to catch the wind. So what on earth stops them from just spinning faster and faster until they literally fly apart when a real storm hits? The answer, it turns out, is a really sophisticated, multi-layered defense system.
And this is where the physics starts to get, well, a little scary. See, while the hub in the center might only be turning at, say, 10 revolutions per minute, the tips of those gigantic blades are traveling a much greater distance with every rotation. If you let that run wild in a gale-force wind, the tip of a 100-meter-long blade could actually start getting dangerously close to the speed of sound.
343 meters per second. That is the speed of sound. And if a blade tip ever hit that speed, man, you're not just talking about a deafening sonic boom. The sheer aerodynamic stress would likely shred the blade into a million pieces. So you can think of this number as the absolute non-negotiable red line. Every single system we're about to talk about is designed to stay far, far away from this number.
So, how do they stay safe? Well, the first and honestly the most brilliant method isn't a brake at all. It's something far more elegant, using the wind's own power against itself through aerodynamics.
There are basically two main schools of thought here. On the right, you have stall control. It's a pretty clever, passive design where the blade is shaped to automatically become less efficient, to stall when the wind gets too fast. But the real star of the show, and what's used in almost every giant modern turbine, is on the left, pitch control. This is an active system that gives the turbine complete, second-by-second command over its own speed.
And here's the core idea behind it. By rotating or pitching each blade along its axis, the system can change the angle that it presents to the wind. You know, it's kind of like turning a canoe paddle in the water. If you hold it flat against the current, it gets ripped out of your hands. But if you feather it, turning it sideways, the water flows right past. That's exactly what the turbine does. It angles its blades to spill the excess wind, shedding all that extra energy and slowing things down, no matter how hard it's blowing.
So, a turbine's entire life really revolves around these three key numbers. You've got the cut-in speed, which is just the gentle breeze needed to get things moving. Then there's the rated speed. That's the sweet spot, where it's making its maximum safe amount of power. But the really critical one for us is that last one, the cut-out speed. The second the wind hits that speed, often around 55 miles per hour, the turbine's mission completely changes. It's no longer about making power. It's about survival.
Okay, so something has to be making all these crucial calls, right? Pitching the blades, sensing the wind speed, all of that requires a command center, a brain that's constantly monitoring everything and making decisions.
And I love this quote from the US Department of Energy because it's the perfect way to think about it. The controller is this onboard computer that's getting a constant stream of data from sensors all over the turbine. Wind speed, rotor RPM, how much power is being generated, and it makes these split-second decisions to keep everything running perfectly.
And here's the most important thing to understand about that controller. It basically has two different jobs depending on the wind. When the wind is below that rated speed, its goal is all about one thing: efficiency. It's thinking, how can I capture every last bit of energy from this wind? But the moment the wind speed crosses that line, its objective does a complete 180. It flips into protection mode, and its only thought is, okay, how do I start shedding this excess energy to keep from getting damaged?
Now, that blade pitching system is the main workhorse. It does most of the heavy lifting. But what if you need to stop the turbine completely for maintenance? Or what if something goes wrong? Well, that's when you call in the heavy-duty backup, the brakes. And a modern turbine actually has a few different kinds. You've got the aerodynamic braking, which is really just that blade pitching system we've been talking about. But there are also electrical brakes that can use the generator itself to create drag. And then you have the big one, a powerful mechanical brake, pretty much like the disc brakes in your car, just on a much, much bigger scale.
And right here, you can see how that all fits together inside that big housing at the top, the nacelle. That mechanical brake, which is usually a massive disc and caliper system, is sitting there on the high-speed shaft, ready to go. It's a powerful, physical failsafe designed to bring the whole thing to a dead stop if needed.
But I think this quote from an actual turbine technician is just fantastic for putting it all in perspective. Even though those mechanical brakes are super strong, they're not what the turbine uses day-to-day to slow down in high winds. That job is for the much gentler, much more sophisticated blade pitching. The brakes? They're really the last resort, mainly used to just lock the rotor in place so a technician can safely work on it.
So when you put all of these pieces together, what you've got isn't just one single safety feature. It's this intelligent, layered defense system that makes sure these giants can stand up to pretty much anything nature throws at them.
It's really this beautiful hierarchy of control. Your first line of defense is the constant, tiny adjustments of the blade pitch. Your second layer is the controller, that brain that's always watching and deciding what to do. And then, your final, ultimate safety net is that fail-safe mechanical brake, just sitting there, ready to lock everything down if it has to.
And this, right here, is probably the most important thing to take away from all this. Seeing a turbine stop in high winds doesn't mean it's broken. It means it's smart. It is a self-preserving machine doing exactly what its designers intended, protecting itself so it can be ready to generate clean energy for years and years to come. It's a feature, not a bug.
Which, of course, brings up a pretty fascinating question for the future. As we build turbines that are even bigger, even more powerful, and put them in more extreme environments, how are these safety systems going to have to evolve? What kind of new materials or smarter computer programs will we need to keep the next generation of these clean energy titans safe?